Today we start a new chapter in substitution reactions. But before we jump into the reactions, we should get familiar with the elements that are going to be part of them. An alkyl halide is a molecule that contains a halogen atom bonded to a carbon. That carbon is sp3 hybridized. The halogen atom it's usually expressed with the letter X. And alkyl halides can be classified as primary, secondary, or tertiary, depending on the carbon that they are connected to. So for example, right here, this carbon that is connected to the chlorine, that carbon is a secondary carbon because it's connected to two R's. So because of that, that will be a secondary alkyl halide. This carbon right here is connected to three R's, therefore this alkyl halide will be tertiary, and this one right here, that carbon is connected to only one other carbon, and so that's why this fluorine will be a primary alkyl halide. Pause the video here and try to figure out what this alkyl halide will be. This alkyl halide will be a tertiary alkyl halide because the carbon that is connected to the X is connected to three other R's. There are different types of alkyl halides. The vinyl halides are the ones that are connected right to a double bond. That's a vinyl halide. And then we have the aryl halides, and those are the ones that are connected to the ring. So the halogen is connected right into the ring or right into a double bond. These type of alkyl halides are not going to be useful for us in this chapter. We're going to see them later on in the course, but they are not going to react in substitution reactions. However, we have this set of alkyl halides that look very similar to the ones in the previous slide, but these are going to be reactive in substitution reactions. An allylic halide is this one right here. See, it's not directly connected to the double bond as it was in the previous slide. This one, the allylic, it's connected to one carbon that is connected to a double bond. So please notice the difference. The one in the previous slide looked like this one, and the allylic halide has a carbon in between the double bond and the halide. On the other side, we have the benzylic halide that again doesn't look like the one that we saw in the previous slide. A benzylic halide has a carbon in between the ring and the halogen. You've seen this before, but let me remind you how we name alkyl halides. To name alkyl halides, we will simply use the same rules that we've seen so far. So you will look for the longest possible chain, that in this case is this one right here, is a heptane molecule, and then you will number it, starting from the side where your substituents will fall into the lowest number possible. So in this case, we will start from the right, just like this. 1, 2, 3, 4, 5, 6, and 7. And at that point, you simply have to place the substituents in the numbers that they are telling you. So if we have a chlorine at position 2, then we will say that at the end. So here we have a 2-chloro, and then we have a methyl at 5, so that's why we have 5-methyl heptane. So for halogens, we have chloro, bromo, iodo, and fluoro. The common names are often used in alkyl halides. So to assign a common name, you simply name the carbon atoms that are in the molecule and add the halogen that is bonded to that alkyl group. So for example, here we have a terbutyl group. So that is going to be terbutyl iodide. Or here we have an ethyl because we have two carbons. So that is going to be ethyl chloride. It's very simple. Alkyl halides, one of the characteristics that they have is that they are polarized, because remember that halogens have their electronegativities are high. So that means that the halogens are pulling electrons away from the carbon, making that carbon electrodeficient. So that's why we have delta plus there. And the chlorine has the delta minus because that is the most electronegative atom in the molecule. And as you can see here, that creates a dipole moment, and so that's why these type of molecules will have dipole-dipole interactions. Because there is a dipole in the molecule, they can interact with other molecules that also have dipoles. So the delta minus will interact with the delta plus from the following molecule, and so on. So here you have some of the physical properties of alkyl halides. They're just an extension of the physical properties of alkanes, but alkyl halides have higher boiling points and melting points than simple alkanes. Their boiling points and melting points increase with the number of R's. So in here we have 2 carbons, in here we have 3 carbons. So the one with more carbons is going to have a higher surface area, and so it's going to have a higher boiling point and melting point. That is exactly what we saw in alkanes. The higher surface area, the higher the boiling point and the melting point. And so as the size of the halogen that is attached to the alkene increases, we're also going to have higher boiling points and melting points. And so here you can see a representation of all the halogens, all the alkyl halides that we can have with a CH3. So here we have methyl fluoride, methyl chloride, methyl bromide, and methyl iodide. The electron deficient carbon here is where the reaction is going to happen, because the electrons are being taken by each one of the halogens. So here we're going to have a delta minus, and here we're going to have a delta plus. So this side here on the left side of these molecules, the delta plus, is going to become our electrophile.